Okay, let's try one more example here. Let T be the boundary of the tetrahedron capital E formed by x equals 0, y equals 0, z equals 0, and 2x plus 3y plus 5z equals 60. If capital F arrow is the following vector field, so y times sine of z squared, whoops, comma, oh sorry, minus x squared, that's all part of the first component. Now there's the first comma, comma, x plus 1 quantity to the zth power minus y, comma, 10 times z plus y to the y to the y to the y to the x. Okay, if this is the current of water at each point x comma y comma z. I mean, we could have said this was a capital F of x comma y comma z. We just have left out the of x comma y comma z. Then how much water is entering the tetrahedron capital E through its boundary capital T? Okay, so E is the tetrahedron itself. E is the solid tetrahedron. It's formed by four planes, x equals 0, y equals 0, z equals 0. And this plane, 2x plus 3y plus 5z equals 60. And the funny language here is that it's how much water is entering in, right? So the orientation is not the outward orientation. Oh, geez, what do we do about that? Well, okay, flux of F, right? How much water, so coming in through T, okay, flux of F across T, this should be the double integral over T of F dot D bold S. Here's the issue though. The orientation is not the direction we want. We don't want how much water is coming in. We don't really want to compute that. We want to compute how much water is going out. But, well, if it's in versus out, all we're doing is just, there's going to be a negative sign here. So this will be an integral over, let's say, negative t. I hope you get what I mean by this kind of silly notation. We'll fix it in a moment. So by negative t, we're trying to just say s is equal to negative t. And all I'm trying to do with this is say S is oriented outward. The usual orientation, the compatible orientation for applying the divergence theorem. Okay, so then let's still copy this minus sign that's here, right there. But then instead of writing an integral over negative t, which is kind of just looks silly, let's just put an s there. Okay, of f dot ds. Okay, so then I'd like you to perhaps think of, well, the whole point here was another excuse to practice the divergence theorem, right? So again, copying the minus sign, okay? And then we'll have, replace this integral, since we've oriented the surface S outward, this should now be the triple integral over the solid tetrahedron E of the divergence of F. Okay, dv. Maybe if you'd like, it would be helpful to just pause the video for a moment and kind of give it a try on your own from here. See if you can implement this dv as, a dx dy dz or dz dy dx or whatnot. Figure out what the bounds of the integral are, compute the divergence, etc., etc. Maybe pause the video for a second. Okay, well here's what I have. Let's just take the work from here. And then we'll have equals, I'll copy the minus sign. triple integral over the region E. And what does the divergence of f look like? Well, it's a good thing when you differentiate the first. So remember the divergence is really a dot product, so the result should be a scalar. When you differentiate this with respect to x, you just get negative 2x. Okay, that's good. When you differentiate the middle term with respect to y, you just get negative 1. Okay, good. So this x plus 1 to the zth power, that's all gone because that looked a little weird. And then the last component, you differentiate with respect to z and you just get 10. So plus a 10 here. That's good because I didn't really want to deal with the y to the y to the y to the y to the x part. Okay, dv. If we clean this up a little bit, okay, let's go ahead and, distribute in this minus sign and have triple integral over e of 2x minus 9 dv. Now all that's really left to do is to implement, and now this is really just a chance to practice some things from the past, right? So let's just say we're gonna commit right now to do this as to write dv as dz dy dx. We'll go in reverse order of the letters, and so maybe just as a quick picture, x-axis, y-axis, z-axis. You can work out based on the most interesting of the equations that define the tetrahedron that there's an x-intercept of 30 and a y-intercept of 20 and a z-intercept of 12. Yeah, just by choosing the other variables. So to get the x-intercept, choose y and z to momentarily be 0. Yeah, so picture certainly not to scale. We've got the triangle. We've got all the points that are behind that triangle down into the origin. So those now, I guess the 4 points highlighted form the vertices of the tetrahedron. So based on the equation up here, for a fixed x and y, we can get what z should be. Z should be at its smallest always equal to 0, but at its largest value should depend on what x and y are. And so if you just solve for z, what you have at its largest, z should be 60 minus 2x minus 3y over 5. Then we should take this here and project this onto the xy plane. And we can basically see what the projection is going to be right here in the picture. It should be that triangle that's outlined there in red, well, shaded in though, right? So if we were to draw that just more carefully in the xy plane, we should still have this x-intercept of 30, this y-intercept of 20, and we're talking about that right triangle here. Since we are choosing to do this as a dy dx, so for a fixed x value, okay, maybe we'll switch here. We want to know what's the smallest, for that fixed x value here, what's the smallest y and the largest y? Well, the smallest y, no matter which x you pick, should still just be 0 always, but the largest y depends because it's given by this line right there. Now that line, by the way, we'll work this out offline, is y is equal to 20 minus 2/3 x. So we can say now, yeah, that y is at its smallest always starting at 0, but at its largest ending at 20 minus 2/3. Oops, minus 2/3 x. Then when you project this to the x line, I guess, so I'm trying to use this language instead of xy plane, the x line, the real number line, you have 0 to 30, and so you've got that, yeah, just filled in there. Okay, so we're going to have x from 0 to 30. Okay, so that means in the end we've got this integral right there. Let's copy this down. Should be integral, leave some space, of 2x minus 9. The dv we decided would be dz dy dx, and that's the order we work things in. So this information here goes right there, 0 to fraction 60 minus 2x minus 3y all over 5. The y is the middle one, so this information goes on the next integral, 0 to 20 minus 2/3 x, and then the x info is right here, 0 to 30, 0 to 30 right there. Well, this integral isn't so bad to do. Let's not finish this any further. Let's call this done right there. Just as an interactive question, let's ask the following. Okay, so by using the divergence theorem, so on this problem, by using the divergence theorem, the question of finding the flux of the vector field turned into computing one triple integral. Right here, one triple integral. Either there, written as an iterated integral, even here, it's a single triple integral. How many surface integrals would you have to compute if you found the flux of this vector field directly instead of using the divergence theorem? Okay, so by using the divergence theorem, the question of finding the flux of this given vector field turned into computing one triple integral. On the other hand, how many surface integrals would you have to compute if you found the flux of this vector field directly across the surface T instead of using the divergence theorem? So that is, going back to this question, if you were to do it directly, let's say you didn't know the divergence theorem, there'd still be a way to do this question. How many surface integrals would you have to compute?